All right, so in this lecture we're moving on to chapter 16, which is kinetics using impulse and momentum. This is our third part of 3 total analysis techniques we're going to do for kinetics. Right, remember kinetics, talking about and analyzing the forces that are responsible for the description of motion and the changes in motion that we talked about in kinematics. 2 main components of dynamics, which is the name of the class here, right? All of these analysis techniques, all of our kinetics stem from Newton's second law, which is where we sum up the external forces on a body, external forces on a particle, and that equals it's the mass of the particle or object times its acceleration. What we've done so far with kinetics, right? We took the Newton's second law, force equals mass times acceleration, directly as a vector relationship. We talked about how we could relate the forces to the changes in motion through time as the particles move through space. We then did some tweak to that and got to work energy, which relates scalar quantities of energy at 2 states to then compare velocities, heights, and maybe string lengths at or spring lengths, sorry, at 2 different states, 2 different times, 2 different positions, whatever you want to call it. And then our third one, which we're moving into today, is the impulse momentum. Okay, which this one will relate momentum before and after an impact between maybe 2 particles, between 2 bodies, or collisions. Okay, and so to further drive home the point that this all stems from the same fundamental principle, I mean, it's in the name here, right? This one just is force equals mass times acceleration directly. Work energy, we took the force equals mass times acceleration relationship, and to both sides we took an integral after we dotted it with little changes in the path direction, dr. And when we move into impulse momentum, and so then this produced a scalar relationship, whereas this was a vector relationship. Impulse momentum, we're going to keep the vector relationship. We're going to integrate this through time. Integrate the force equals mass times acceleration, do a different kind of integral, and do it in time. And that's going to produce a different method to be able to analyze the systems and or analyze the dynamics of a system, or just maybe a single particle. Okay, so let's dig into it. We'll see how that works, and we'll compare it along the way. So we start with Newton's second law, as we did all here. Sum up the forces equals mass times acceleration. We'll be more careful with it than we were up above here. This is more general and more of a summary and reminder of where we are in the course. All right, so acceleration is just dv dt as a vector. And so what we want to do now is integrate this from time 1 to time 2. So from time t1 up to t2. Okay. And so what that looks like is we will sum up the force over this time, and that equals mdv, right? When we integrate the right hand side over dt, this becomes just a differential velocity. Okay. And well, that, since mass is just assumed to be constant, not changing as we go from time 1 to time 2, that's just like the mass of the object of interest. This is just a difference, so this is a differential velocity. Macro scaled as we do the integral here is going to be the difference between the momentum in the 2 states. Okay. So there we have it, right? Not too tricky there, but now there's some analysis we need to do, or some discussion maybe we need to have about what these terms are. First thing, we'll just make some observations here. This is just like the original relationship. This is a vector equation, vector relationship. It's not like work energy, which is a scalar. And the units here are, well, we can interpret it as a Newton for a force, so a force times a time, so it's a Newton second. Or over here we have a kilogram meter per second, right? And those should align. So we have a Newton second or a kilogram meter per second. and those are the same thing, right? Or if we're in U.S. units, U.S. customer units, this is a pound force second, right? And what this says now, right, is that force acting over time, that's why we, integrating a force through time, causes a change in this quantity, m times velocity vector. Well, that's just momentum. So a change in linear momentum. Right? Where, now we can actually put some names on these quantities here. When we integrate something through time, we call that a linear impulse. It's just the total amount of force integrated over time. And that's a vector quantity, right? And then mv is the associated linear momentum that is changing due to that impulse. Okay, so that's why we call this impulse momentum. All right, so let's well, we're going to talk about both of these, but let's take a little bit of time to just talk about impulse and what it means to integrate a force over time. And we'll just take this as a scalar quantity, meaning like let's look at the force in one component, assuming it just kind of it could change over time, but we're just going to analyze a single component of this. Okay. So linear impulse is, well, we just had it there, but since I closed it, right, let's just say some component of the force integrated over time. Okay? One component of the vector quantity. Okay. So, well, if we're integrating a function, f, or the force, which we can think of as a function, over time, let's plot what the force is over time and make up kind of what the force is, right? Maybe you're pushing something with some random noise here, but pushing on it harder and harder and harder through time, right? That's what this would mean. So what we're doing here is we're taking the force at some time 1, right? Or the time at some t1, and later on deciding when we're going to end our calculation, our measurement of how much force is applied, and then integrate this or take the area under the curve. Area under curve is what we call the impulse. It's really an accumulation of force over that time, the time range t1 to t2. Okay, so then we can have something called an impulsive force, which is going to take on a specific nature, right? And this is often where we use analysis of linear momentum, is when a force is impulsive. So it has this kind of like slow changing nature to it here, over a macro time scale here. That's changing. It's not so useful to because then we have to go through the process of actually integrating this. But if we have an impulsive force, right, this is something that acts over a very short time, but has significant impulse. All right, so significant. Another way to say that is it has significant impact on the momentum of the thing being forced on, right? Feeling the force, impact on the momentum. Okay, so an impulsive force, like the diagram we have here, we'll reproduce that diagram, but for an impulsive force, it will be much more localized, right? Basically, no force, no force, no force, and then we'll have this really rapid, violent force that then quickly decays to nothing. Okay, and so again, the area under this curve is the total impulse. All right, and now let's do something here where maybe it still would be categorized as impulsive, but, and this is the total impulse due to this force, right? Meaning we could come out to here and this is T1 and out here is T2, and that's the impulse is really the entire force that was ever provided by by whatever's causing it. So let's do a second one here. These are both force. We kept the units the same there. So what we're trying to do is like look at what two collisions or what two impacts look like that have equal impulse but do have some different characteristics. Okay, so in order to have the same impulse, we better draw something with the same area, but maybe it's going to be spread over longer time, right? So maybe it's like here and then decays away. All right, and maybe these definitely aren't the same area. So if I really wanted to make these the same, maybe I scratch this one and maybe we'll use that one and that one. I'm more convinced that these are the same area, these inner ones. Okay, so ignore the outer one. We'll overwrite it in green. And then green. Okay, I think that looks better. Maybe this bottom one still has a bigger impulse, but try to keep it on the same time scale here. Regardless, we've shrunk down our total force, right, to make sure that the area is approximately the same. So if we're going to have the force go over a longer time, right, then the force magnitude needs to be less in order for it to be the same impulse. Okay, so let's see. These two then, we're trying to make them look like they have equal impulse. And we notice that as the total, delta t here, we put in our t1 now is way out here, and t2 is further up there, right? Where delta t is the change over which it's acting, right? Over which the force is acting, that we're taking the integral. Our average force has to be going down, or in this other case as delta, oh, and I forgot, delta t goes up. If delta t is lowering, like we're doing in this process here, the average, sorry, we did the first one, right? Delta t went bigger from here to here, and the average force had to go down in order to keep the impulse the same. Okay, so let's actually put like what this quantity we have here is the average force. And let's put that actually on the diagram. So the average force that acts over this time, might look something like that. All right, so basically the area under the green line I have there should be about the same over this time window, and here it's going to be, maybe something like that. Okay. So this gives an idea of like what impulse is, and we call something impulsive if it has a pretty big impulse associated with it, but over a very short time. So right, so it's a pretty limited, and that's going to happen when we have these like rather violent collisions or impacts. Okay, impact events. So if we then move into something called conservation of linear momentum, we're going to go back to what we said impulse was. Those impulses cause a change in linear momentum. So conservation of linear momentum. Okay, this says is that when external forces to a system can be neglected, and what we mean by that is short but violent, well, doesn't need to be violent, but sometimes and that's a subjective word here, right? But what I mean by violent is that there's definitely some like energy losses going on here, right? You can tell by the change in the material shape, you can tell by there's maybe heat given off here, but if there's short but violent collision between two objects, that's one. No external forces acting on the system as a whole. No external forces acting on the system of objects. And so this is not a good candidate when these collision events are not good candidates to study with work energy, because there's a lot of non-conservative forces in that, like changing the material shape, right? That's energy going into the system that's hard to quantify. There's a lot of heat generation that's hard to quantify, right? But what we can do is with these collision events, we can analyze them through their linear momentum, and as long as we keep it as a confined system, the external forces on a system of objects here is then 0. Okay. So let's step back, right? This is going to be where we're going here. This is like the key to this is dealing with the collection of particles. But let's step back and just consider a single particle for a second, and with this imposition on it, right? And we'll find there's not actually much interesting we can do with that. In fact, we're just going to derive one of Newton's laws here with analysis of momentum. So for a single particle or object, okay, if there's no force or there's no impulse, right? Maybe go back here and label. What we really meant here was 0 impulse. Where did we go? What we're saying here is impulse equals 0. Okay? So we're doing the same thing here now, but for a single particle that's standing, independent, is just the only object to be in consideration. In that scenario, right, this then means, right, this is impulse, no impulse. Well, that's a change in momentum of that single particle by our impulse momentum relationship that we derived earlier. And so what this means is, well, the mass isn't 0, and if it is 0, that's not of interest here. And that means that the velocity can't have changed. Okay? What we're saying here is if there is no acceleration by constant velocity or velocity not changing when that single particle or single object is not acted on by an external force. And so what we have here is Newton's first law showing up as a result of a specific case of Newton's second law. Right? We started with Newton's second law, we integrated it in time, we then applied it to a single particle if there was no force applied, and we got no acceleration. Right? That's Newton's first law. All right. Now let's do for a system of 2 particles and make them nice and big particles. Okay. Okay, and they could be different size, they could be different masses, but there's A and B. Okay, and what we're going to do here is, we're going to actually use Newton's third law, or that principle, to make a statement here. Newton's third law says that, there's we don't know what it is. It could be gravity, it could be a contact force. It could be that these are actually charged particles and they're electrically attracted to one another. But we can just say that if there is some force on A due to the presence of B, then, and these need to be about the same length to graphically show them accurately, then we must have equal in magnitude but opposite in direction force on B due to A. Okay, so force AB, and I'll be careful to define these as FBA, and they're negative, meaning they're going to flip the direction. Okay, let's talk about this notation here. This notation means that the force on A due to B being there, right, or B doing something, right, and then this one is going to be the force on B due to A. All right, so here's now, right, this was when we applied this idea of 0 impulse to a single particle, right, we got, we confirmed Newton's first law. But when we apply it to a collection of particles, or just 2 particles here, right, and keep that as the confined system, what we then find is here, right, the total sum of the forces here are gonna cancel out and be 0. So as a system, we get 0 net force, and as long as there's not some external force outside of this collision event, or whatever the force is that we're currently analyzing here, as long as there's nothing external acting on the system over this time that we're analyzing it here, we have a 0 impulse globally, right? As long as we include them in the same, in the same calculations. So note here, the forces, like I said, could be a contact force, kind of drew them as if they're attractive here. And if they're a contact force, or there could be a spring connecting them, which means the forces could go in either way. But if they're a contact force, usually we would say they'd be in the directions would be wrong here. But that's fine, right? We're just drawing it, keeping it general here. Would be opposite direction in that case. All right, what we mean if they actually are in contact with another, that would be like a normal force where B would push on A, and that force would be in the other direction. FAB would be that way, and the force on B due to A would be the other direction. Yeah. Okay, it's just something to keep in mind. But here we just kept it general as just some force, and then therefore it didn't matter which direction we drew it. All right, so let's see here. Let's apply impulse momentum to each particle here independently. Okay, so this is going to be the impulse momentum relationship for each separately. All right, and remember what that says is we are going to take the integral over some time of the force on A in this case is going to equal the change in momentum for A. So, right, integrate that force through time that's on A is going to be the change in A's momentum. So we got its velocity at state 2 for particle A minus the velocity at state 1 for particle A, right? And then we have the same thing here for BA. That force is felt on particle B. We got the momentum at B at 2 minus the momentum of B at 1. Okay, now the trick is, well, if we're going to analyze the system as a system of two particles, well, then we can, what we're really doing here is adding these up together, right? Adding these two relations together, right? Well, if FAB is minus FBA, then this summation here is going to cancel. That's where the 0 comes from. And then we get MAVA2 plus MBVB2 minus MAVA1 plus MBVB1. So this is the impulse momentum for the system. For system of two particles. Okay, and let's let's make it nice and neat, which is no negative signs involved here, right? So pull the initial state to the left-hand side and leave the second state, state 2, after the collision over here, and that'll be the form that we'll box, right? That's the prettiest one. Okay, and that's what we'll go with. So here, what we have in this mathematical expression, we have the momentum at time t1. This is typically chosen, the time is chosen by the analyzer, so us, right? The one doing the analysis of the mechanics. Before the collision, that's when we choose time 1 to be, and then we typically choose time 2 to be the moment that the collision is over, t2, after the collision. And that's a good choice, because doing any other analysis while the collision is going on is going to be tricky, because it deals with the complicated, loss of non-conservative, the energy loss due to non-conservative forces. This is a vector equation. Make a few observations here. We've got a vector equation, and typically there's too many unknowns to actually solve this, and so we often we make some assumptions along with this. Too many unknowns, so we need more, at least one more usually, relationship. And we'll wrap up our discussion here in this video with this extra relationship can come from assuming an elastic collision, perfectly inelastic collision. But in general, right, we make some sort of statement about what the final state is compared to the initial state, and the most general way to say that is through this thing called the coefficient of restitution. And so beyond just momentum being conserved before and after a collision, there's actually some relationship between the two objects in terms of their velocities. And so we call it E, all right? Coefficient of restitution is E, which is the difference in the final velocities over the difference in the initial velocities, right? It kind of gives a measure of the relative amount of change in the difference in the velocities, right? Okay, so let's make some statements about this. This is thought of as a material property, okay? And so what we mean is if we're dealing with the material in the two objects are lead, we're going to have a different value here than if it was made out of steel or like wood or something of a much different material nature. If E is 1, that is the case of an elastic collision. And what an elastic collision is in addition to conserving momentum, we also conserve kinetic energy. And so we would say, in addition to this being true, momentum being conserved, in addition to that, we also impose on the system that KE1 equals KE2, or 1/2 mv squared equals, I guess this is the total kinetic energy of the system, right? The other extreme here is when E is 0.0, and this is the case where we're actually maximizing the kinetic energy loss, right? And what we're basically saying is there's no difference in the velocity in the final state, right? So that's the way to minimize basically kinetic energy in the final scenario. This we call a plastic collision. I always remember calling it a perfectly inelastic, so that's a fine way to categorize these. Inelastic just means not elastic, so anything but an E value, a coefficient of restitution of 1, anything but 1 is going to be inelastic, but if we drive it all the way down to 0, that's perfectly inelastic. And this is a scenario where the two particles stick together in the final state, and so VA2 equals VB2. That's the extra. So if we're talking about the extra relationships that we're needing, right? These are often we're making an assumption, something like this, and then I already mentioned this is the maximum kinetic energy loss that is possible. Okay, and last statement here. This is often an experimentally determined quantity or measured in a lab for like particular materials and particular scenarios, right? Okay, so next up we'll be doing examples of this linear momentum conservation for collisions.